Welcome to this video about Lasso regression. In this video we'll see how Lasso regression works. We'll also learn how to find an optimal value of lambda based on cross-validation. At the end of this video we'll see the difference between Lasso regression, ridge regression and elastic nets. If you're not familiar with how ordinary least squares works, I suggest that you have a look at my second video about linear regression. Ordinary least squares regression cannot be computed if the number of parameters to be estimated is larger than the sample size. For example, if we have only 2 data points, we can only estimate a maximum of 2 parameters, the intercept and the slope. However, if we only have 1 data point, we can only estimate the intercept because 1 data point is not enough to say anything about the relationship between 2 variables. With just 1 data point, there can be an infinite number of possible values of the slope. Lasso regression belongs to a group of methods called regularization regression methods, which can deal with the challenge to fit them all even if we have fewer data points than the number of parameters that we like to estimate. This means that we can fit them all with more explanatory variables than the number of data points we have. Lasso regression can also be used for feature or variable selection, since it shrinks parameters associated with less important variables to 0. Suppose that we have the following dataset, where we like to see if we can predict the systolic blood pressure with the explanatory variables age and score on a certain math test. For example, we see that person number 1 is 22 years old and has a systolic blood pressure of 120. Out of the 7 individuals, person number 1 got a score of 65 on the math test, which is the highest score among the participants. Let's plot the blood pressure against age. Based on this figure, it seems like older people have higher systolic blood pressure. If we fit the following regression model to the data, we can draw the following regression line based on the estimated parameter values. The R-squared value of this model is about 0.58, which tells us that age explains the variance in the blood pressure among the 7 individuals pretty well. Now, let's instead use the math score as the explanatory variable. It seems like a higher score on the math test is related to a lower blood pressure. This sounds a bit strange, because your knowledge in math should not affect your blood pressure unless there is some strange underlying relationship. However, the R-squared value is very low, which tells us that the variable math score is not that good in explaining the variation in the blood pressure. In addition, if we compute linear regression, we see that the slope associated with the variable math score is not significant, which indicates that the negative relationship we observe is just due to chance. If we create a model including both age and math score, we'll get an R-squared value of about 0.59, which is greater than if we use only age as the explanatory variable. This tells us that a model including both age and math score fits better to the data and explains the variance in the blood pressure better than if we only use the variable age. However, this is one problem by comparing models by using the R-squared value, because a model with more parameters will always fit better than a model with fewer parameters, although some explanatory variables are completely useless. In this case, the variable math score is completely useless in explaining the blood pressure, but since the model now has an extra parameter, it will simply fit better because it is now more flexible. It turns out that if we add many useless variables to predict the blood pressure, such as favorite color and favorite car, it is possible to get a model with an R-squared value close to 1, which is supposed to be a perfect model. However, if we use this model with many useless variables to predict new data that were not included to train or estimate the parameters of the model, it will be really bad at prediction. This is what we call overfitting, because the model is very good at predicting the training data, but bad at predicting new data that was not included in the fitting process. Such a model would actually be useless. So this is where Lasso regression comes in, because it can remove variables that are not important for explaining the response variable. Lasso regression is less sensitive to the training data compared to ordinary linear regression. Lasso regression can remove less important explanatory variables by minimizing the following function. This part of the expression is simply the sum of the squared residuals that we have discussed in the previous video. Remember that y sub I is the value of the observations, which in this case is all the blood pressure values of the 7 individuals. Whereas y hat is the y value of the regression line for the corresponding x value of the given observation. The difference between the observed and fitted values is called residuals, which corresponds to the vertical distances between the regression line and the data points. In our case, we have 7 residuals, and if we sum the square of these residuals, we'll get the sum of the squared residuals, also called the sum of squared errors. We divide this by n, the sample size. So we get the mean sum of squared errors, because it is then easier to compare models based on different sample sizes. For computational reasons, a 2 is sometimes added in the denominator. What is new is this term, which sums the absolute values of the estimated parameters, except for the intercept. This sum is then multiplied by a tuning parameter called lambda. The value of this parameter is decided by the user and is usually estimated by some sort of cross-validation. We'll discuss how to find an appropriate value of lambda at the end of this video. This term gives a penalty for models with a lot of variables because we will then have a lot of parameters to estimate, which means that this sum will be large. Also, large values of these parameters will also result in a high penalty. If the value of lambda is 0, this term will be 0 and the Lasso regression will be identical to ordinary least squares, where no penalty is given for models with a lot of estimated parameters. If lambda is high, the value of this term will be much bigger compared to the value of this term. This term can be seen as how good a model fits the training data, whereas this term can be seen as how many parameters we have in the model and how large those estimated values are. Lambda determines which of these two terms that is most important when minimizing the function. Although Lasso regression is mainly used when we have a model with several explanatory variables, we'll here try to use it on the following simple model so that we understand how the algorithm works. When we fit this model to the data by using linear regression, we try to find optimal values of the intercept and the slope, so that we minimize the sum of the squared residuals. Lasso regression usually begins by standardizing the explanatory variables. This is because we do not want that a certain unit of a variable should influence the fitting process. For example, to standardize the variable age, we subtract the mean for the 4.7 from all the values, and divide these differences by the standard deviation of the corresponding variable. This is the standardized data where each variable now has a mean of 0 and a standard deviation of 1. For the mere convenience, we'll here also standardize the response variable. If we plot the standardized data, we see that the data points are now centered around 0. The regression line has so far only been estimated based on ordinary least squares, which is this part of the equation. If we try a range of different values of the slope, we see that the mean of the sum of the squared errors is minimal when the slope is set to 0.76. A steeper slope would result in a higher error, which is true also if the slope is less than 0.76. A slope of 0.76 therefore results in the lowest possible mean squared error, which means that the model fits best to the data if the slope is equal to 0.76. Now, let's see what happens if we include also the penalty term in the function. Suppose that this term would be equal to a constant in this case, for example 0.3. Then we would simply get the same curve with an error that is 0.3 bigger than the previous curve. Both curves will have their minimum when beta 1 is equal to 0.76. However, if we include the real penalty term in this function, or we set the value of lambda to, for example, 0.4, the curve that represents the value of this function now has a minimum at about 0.53. This means that the estimated slope would be lower compared to if we use only ordinary least squares. This is because we try to minimize the value of this function, where we shrink the absolute values of the coefficients as much as possible so that we still get a good fit. Since we only have one explanatory variable in this example, p is here equal to 1. And the sum of the absolute values of the estimated coefficients is here simply equal to 0.53, which is the estimated slope according to the Lasso regression. However, Lasso regression becomes a lot more interesting if we have more than one explanatory variable, like in this case where we have 2. We'll now fit a plane to the data that fits as good as possible, with as low values as possible of the two slopes in this case. Since we saw earlier that the explanatory variable math score is more or less useless in explaining the blood pressure, the algorithm will especially reduce the value of this parameter, because that will have a small effect on how well the model fits the data. For a given value of lambda, the estimated value of beta 2 will be reduced so that it is equal to 0. This explanatory variable can therefore be seen as it is deleted from the model. This is the main idea of Lasso regression. It shrinks parameter values, especially for less important explanatory variables, so that they become 0. Let's use the software to fit this model with Lasso regression, where lambda is arbitrarily set to 1.2, and compare it with ordinary least squares, where lambda is simply equal to 0. These are the estimated parameters of the two different methods. Note that the coefficients have been unstandardized, so that they fit the original data instead of the standardized data. We see that both methods have estimated intercept to about 113. Since Lasso regression reduces the absolute values of the parameters, the slope associated with the variable score has been set to 0, and the slope associated with the age has been reduced from 0.35 to 0.28. This reduction will lead to that the model does no longer fit as well to the training data as the linear regression model. However, as we have seen earlier, since linear regression tends to overfit, the Lasso regression performs at least as good or better when applied to a test dataset compared to linear regression. We'll now discuss how to find an appropriate value of lambda. One way to find a good value of lambda is to calculate the mean squared error of prediction by some sort of cross-validation for many different values of lambda. For example, we could perform the leave one out cross-validation where we leave out the data point for the first individual, and then perform Lasso regression on the remaining data with a certain value of lambda. We then use the Lasso regression model to estimate the systolic blood pressure based on the explanatory variables for the person that was left out. Then we compare the predicted value with the observed value of person number 1. Then we set aside the data of the second individual, and compute Lasso regression for all data except for the second individual. We then use Lasso regression to estimate the systolic blood pressure based on the explanatory variables for the person that was left out, and compare with the observed value. We continue like this for all individuals. Then we repeat the whole process with a new value of lambda. We can then generate this kind of figure where the cross-validation error, which in this case is the mean squared error of prediction, can be plotted as a function of different values of lambda. Based on this plot, we can select the value of lambda that results in the lowest cross-validation error. When lambda is equal to 1.42, only one out of the two variables is selected for the null. We can also see how the values of the coefficients change as a function of lambda. When lambda is close to 0, the coefficients are more or less equal to the coefficients in ordinary least square regression. When lambda is equal to about 1.42, the coefficient associated with the variable math score is equal to 0. A too high value of lambda will reduce all coefficients to 0. If you set lambda to 1.42 in this equation, the intercept will be estimated to about 114 and the parameter associated with the age to 0.267. Due to shrinking the coefficients, the Lasso regression has reduced this value to 0, which means that we can remove the variable math score from the equation. Finally, we can use the reduced equation with estimated parameter values to fit a regression line to the data, and use this model to predict the blood pressure of new individuals based on their age. Before we end this video, we'll have a quick look at the difference between Lasso regression, ridge regression, and elastic nets. In comparison to Lasso regression, which sums the absolute values of the estimated parameters, ridge regression instead sums the squared values of the estimated parameters, which shrinks all coefficients towards 0, whereas Lasso regression can shrink the coefficients to completely 0. Lasso regression is therefore a good option if you like to remove a lot of variables from the model. However, if there is a group of variables that correlates, then the Lasso method tends to select only one variable from such a group. In comparison, ridge regression is a better alternative if you like to keep all the variables in the model. For example, if you like to keep a set of good variables. The problem with ridge regression is that it will keep also useless variables. This is where elastic net regression comes in, which includes the best of Lasso and ridge regression. The parameter alpha spans between 0 and 1, which determines how much of the two methods that should be used in minimizing the function. For example, if we would have a third explanatory variable that represents the diastolic blood pressure, which is expected to be a good variable for predicting the systolic blood pressure, then we would have two good variables that are likely to correlate, and one useless variable to predict the blood pressure. The Lasso regression would in this case remove the variable score, but also age, when we use an optimal value of lambda based on cross-validation, whereas ridge regression would keep all variables. For certain values of alpha and lambda, the elastic net would keep both age and the diastolic blood pressure and delete the useless variable math score. Finally, note that we can replace this part of the function with a negative log likelihood function so that the regularization regression methods also can be applied in, for example, Poisson regression and logistic regression. This was the end of this lecture about Lasso regression. Thanks for watching.